Hello everyone, just checking my mic volume. How's it going? Welcome back to Computer Science 3200. Today we are supposed to be talking about genetic programming and assignment 4. And I was looking over the slides, and genetic programming is a nice little niche subset of evolutionary computing. It's quite interesting. But it's not really something that I can really effectively test you on. We're not going to have an assignment on it. It'd be kind of weird to ask an exam question about it. So what we're going to do today, because we've all got enough work to do, right, is we're gonna skip talking about genetic programming. I know it might take a half an hour to do it. It's pretty quick, but let's have one less thing for you to worry about for the exam, shall we? And so I'll just take this lecture. Actually, probably not even close to the full lecture, because assignment 3 is quite conceptually easy to understand, and there's not many instructions. So we'll just look over assignment 4. We'll scrap the genetic programming part of the lecture, and that's how we'll do it. I'm going to very quickly pull up the chat here in case there are any questions, because I forgot to do that again. If there are any questions, let me really quickly pop out the chat from the stream. There we go. All right, perfect. So let's go back. So yeah, today we're talking about assignment 4. For all of you still working on assignment 3, it's due tonight, so make sure you get on that. And assignment 4, again, it's on genetic algorithms. It is probably, other than assignment 1, I think it might be the easiest assignment. The entire difficulty of assignment 4 is how good are you conceptually with arrays in JavaScript, because it's basically everything is just talking about arrays. Applying things to arrays, sorting arrays, going through arrays, it's all arrays, 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 because it's genetic algorithms. You have 3 full weeks to do this assignment, and so you're going to have a bit of time off from working on assignments so much, because this assignment should not take you that long. I think that if you started assignment 2 tomorrow, you could probably bang it out in a day or two. Or sorry, assignment 4. Assignment 2 was quite a lot of work. So assignment 4, I think that in terms of actual programming, is by far the least amount of work. Maybe competing with assignment 5. But anyway, let's get on with the assignment. So here is the user interface that you are going to have with your assignment. So what we are going to do, the end goal of this assignment, is to write the functional parts of a genetic algorithm. And what we are going to do with that genetic algorithm is try and solve a Sudoku board. So Sudoku is a puzzle game. If you are not familiar with the rules, where have you been? But that's fine. You can go look up the rules if my explanation isn't very good. But essentially, a Sudoku puzzle is a puzzle with a specific size. So this is a 9x9 Sudoku board here. And your goal as a player, typically when you are given a Sudoku puzzle as a person. Okay, you know what? Let's go solve a Sudoku puzzle. Let me find a website. Sudoku puzzle online. Here we go. Let me find one. Sudoku.com, apparently. All right. So here is a Sudoku puzzle. It is of easy difficulty. And what we have to do with a Sudoku puzzle is typically we are given a partially filled out board. Okay, for our assignment, we don't have a partially filled out board. We are just trying to generate a full board with a genetic algorithm. But what we have here is a partially filled out Sudoku board. And now the rules of a Sudoku board are that each row, each column, and each of these sub-squares have to contain all of the numbers from 1 to 9 exactly once. So for example, if I put a 1 here, it's going to tell me you can't have a 1 here because there's a 1 conflicting in this column and there's a 1 conflicting in this row. If I put a 7 here instead, it will say, oh look, there's a 7 in this square as well as a 7 in this column. So the way you typically go about filling out a Sudoku board is you would say, all right, where could I put something that doesn't have any conflicts? So for example, let's erase that number that we put in, And now we could look over and say, oh, look, this column has a lot of numbers already filled in. What numbers aren't there? So we have 1, 2, 3, 4, 5, 6, 7. So in here or here, it's either going to be an 8 or it's going to be a 9, right? So we could put an 8 in here, or we could put a 9 in here. Why can't we put an 8 in there? Is it telling me there's a conflict? I don't know, but it's telling me what the conflicts are. So I could put an 8 in there, or sorry, a 9 in there. I could put an 8 in there. So I've completed this row. This particular easy version of the game is actually going to tell me when I'm right or wrong, but usually you won't be specifically told when you are right or wrong. So what you do is you figure out, okay, I have this could be this or this or this, so I'll put in a number here. So that's the game of Sudoku. Your goal is to fill up the entire board. Here, instead of starting from a partially filled out board, you just are starting with a random full board, right? And so if you see at the beginning, this kind of looks random, and then your genetic algorithm's job is to mutate, recombine, and just fill out a solved Sudoku board, okay? So you can see here that in the user interface that I've given you, there are a number of things. Over here on the left, this shows the current highest fitness individual from our population. So that's what this is showing. And over here, now this is the solution code, so it's running properly. I have a graph which is updating in real time as the generations are happening, okay? So on the x-axis here, we have the generation number. Let me make that a little bit bigger. And on the y-axis, we have a fitness value. Over here, you can see that I'm keeping track of 3 different values. One is the maximum fitness of any individual in the population. And it just so happens that the thing that has this maximum fitness is over here on the left-hand side. We show the average fitness of the entire population, and we show the minimum fitness of the entire population. I'll go over what the Sudoku fitness is a little bit later, but just realize that essentially what happens is that if your genetic algorithm works correctly, you should have curves that kind of look like this, with the maximum fitness going up over time, as well as the average fitness, and which I'll talk about later why our minimum isn't going up, but it's essentially because we're inserting some random genes in every population. Now, over here, you can see that for the Sudoku visualization, I have some colors here, right? So just as I showed in that previous website, the colors here are showing the conflicts of every number. So that means that if something is just white, there are no conflicts in the row, column, or square. If it's a light red, then there is one conflict somewhere. So for example, this one right here has a conflict right here with this one, but nothing in the column and nothing in the row. And you can get darker colors as well, up to, so 0, 1, 2, or 3 conflicts. And that is what's being showed here. It's just a quick visualization to see sort of how many numbers are in a place where there are no conflicts. All right, down here, I have different controls for the genetic algorithm. And the cool thing is you can actually modify these controls in real time as your genetic algorithm is running. So the first thing we could do is actually change the size of the Sudoku board. So you see here, if I reduce the Sudoku board, Sudoku can take any number, right? Traditionally, it's played with 9 values. So this 3 here means 3 by 3 squares, or 9 values. Here, this is 2 by 2 squares, or 4 values. So here you can see that the genetic algorithm runs for a little bit, and eventually, hopefully, does solve this. Sometimes it gets stuck in a local optima and doesn't solve it. There we go. So we solved a 2 by 2 Sudoku board. A 1 by 1 Sudoku board is not very interesting, but I can also go higher to like a 16 by 16 Sudoku board if I want to, and it will try and solve that. But what I want to show real quick is that I have programmed in a number of different fitness functions. And your genetic algorithm, GAs are so cool because the algorithmic process of optimization is entirely guided by your fitness function. So I can solve an entirely different problem with the same algorithm just by changing my fitness function. So if I look here in this drop-down menu, I've got a number of different fitness function programmed in. One of them is called sum values. And so we're not going to be doing Sudoku anymore, but with the same algorithm, if I change this to sum values, then what the GA is doing for its fitness function is just summing up all the values in the array. And so you'll see that over time, these values are going to increase and increase and increase, right? And so you'll see that if 1 to 16 is the range of values that can be input, then eventually everything will get to 16. And you can see over time how our maximum fitness is going up. That's pretty neat how we can do that. If I change this back to 3, you'll see very quickly that since 9 is the highest number that we can have, very, very quickly this GA solves putting 9s everywhere, because what it's trying to do is maximize the sum of the values on the board. And already, pretty much, we've gotten all 9s on the board. What's the next one? So I've got another one here, which is called match row. And what that does is it's going to try and insert, so match row, it says add 1 if the number in the cell matches its row count. So up here, this 1 is in the first row, 2 is in the second row, 3 is in the third row, 4 is in the fourth row, right? But all I've done to tell the genetic algorithm to now solve this problem, and you can see here it's having a little bit of a problem with changing that last 2. So what I'm doing, maybe I'll bump up the mutation rate a little bit. There we go. So what it does here is it's the same algorithm. It's the same GA with a different fitness function. Now, if I want to match the column instead of the row, then it will do that as well, right? So the really cool thing about GAs, to repeat, is that it just maximizes the fitness function. And if you put in a different fitness function, then it's going to solve that problem. And so the last one I have here is just a checkerboard. So I just add 1, I think it's 1s and 9s in a checkerboard pattern. And so what I've done is just add 1 if the 1 or the 9 is in the correct spot. And what you'll see over time is that it does form this checkerboard pattern. And I know that these are sort of trivial examples. They're way less difficult than the Sudoku problem, but these are here to test your algorithm for you. So before you start working on your Sudoku fitness function or whatever, you can just come down here. Once you've written your GA, which is the first thing you'll do, you can come down here and click sum values, and you can see whether or not your GA is working, because it's an easier problem. It's a convex problem. We talked about that before. There is only one optima, and that is the global optima, so you can always get to the global optima. There's no local minima or local maxima for you to get stuck in. So it's a really easy problem for a GA to solve. Okay, so that's the fitness function part. Now, there's all these other things. So the population size, that's pretty self-explanatory. If I drag this up, let's say I drag it up to like 500, then my population will contain 500 things. And as you can see, my GA has actually slowed down a little bit because it's harder to work with 500 things than it is to work with 100 things. Okay? Down here, I've got my mutation rate. That mutation rate is going to go into a settings object. So all of these things go into a settings object, which is accessible by your code, and you will read that settings object and run the GA accordingly. I just want to show the UI before I get into that stuff. So this is the number of individuals that are mutated. So if I restart this and go back to sum values, let me put up a bigger problem, okay? So the number of individuals mutated, this is the percentage. So right now, 20% of our offspring are being mutated before they go into the next generation. Depending on your problem, you may want a really high mutation rate. You see, as I put up the mutation rate here, in real time, my fitness curve actually went up. Because for this problem, we want a really high mutation rate. So let me just show you that again. So down here, I'm going to click sum values, and I'm going to put the mutation rate down to like 4% and then bump this way up. So with a low mutation rate, it's very infrequent that we are actually changing the individuals in our array before they get to the next generation. And so you can see here we've got a pretty steady increase with our fitness function over time. But if I bump up the mutation rate, we're going to get more changes, and very possibly our rate of increase is going to, that line is going to get a little bit steeper. Maybe I waited a little bit too long for this one, but sometimes for some problems, yeah, there's a little bit of an increase here. It's a little bit steeper here than it was. So depending on the problem, you may want to add more random individuals or not. Down here, this is the number of random genes that we insert at every population step. So in order to keep the gene pool a little bit fresh, what I'm doing is saying, okay, I've got a population size of 100. On every single generation, the first thing I'm going to do actually is input 5% random genes. So 5% of 100 is 5. So every population is going to be given 5 completely random genes to keep that gene pool a little bit fresh. So down here, what we see is the maximum fitness is rising over time. And because the maximum fitness is rising, so is the average fitness. But the minimum fitness is staying the same. And the reason that the minimum fitness is staying the same is because we are inserting random genes on every population, right? So if I said I want 0% randomness, right, then no random things would be inserted on every population, and we would immediately see the minimum jump up, right? And that's because all of our genes now are being generated through parent selection and recombination and mutation, and there are no completely random things. So you can see that because I'm not putting any really bad random things in, then, all right, the minimum fitness has shot way up, and accordingly, the average fitness has shot up as well, all right? By the way, these are really good exam questions. For example, what would happen to our fitness over time graph if I increased the random number of genes? So, for example, if I'm looking at the average curve here now, if I increase the random genes to, say, 50%, then quite obviously, the average value is going to go down because a random gene typically has a really low fitness score. So if I have a really low fitness score for random genes and I'm putting a bunch of random ones in, then the average score will go down. But if I put no random genes in, then the average score is going to go way up, right? Okay, so I'm going to reset this a little bit, put it back up. And the last thing that we have is elite gene survival. So what this does is it says, I'm going to take the top 10%, because it's currently set to 10, I'm going to take the top 10% of all of my genes with the highest fitness. So I'm going to take my population, figure out all their fitnesses, and then sort the population based on fitness. And the top 10% of those high fitness genes are going to just be copied into the next population. So what that means is that I am always going to guarantee that my fitness, my maximum fitness, never goes down. Because if I'm taking the best few things from every population and guaranteeing that they survive, then my maximum fitness can never decrease. However, if I turn that off and put it down to 0, then I am not guaranteeing that my maximum fitness individual survives. And you can actually see that what this can do a lot of the time is that if we're just doing straight linear roulette wheel selection, it is not guaranteed that our maximum fitness person or individual survives over time. And so our maximum fitness may actually go down unless we keep a few of the top ones around, at least one. And if we do keep a few of the top ones around, then we're guaranteeing that our fitness is going to our maximum fitness is not going to decrease because we're always keeping the best one. All right. And it's kind of cool, I think, that you can see these going in real time as you're running your GA. And the reason for that is because every generation reads in the settings and does its own thing. So on one generation, you could have one particular set of settings, and on another generation, you have another particular set of settings. And what I've done is this UI in real time modifies that settings object so that you can see its effects in real time in the graph. So on the final exam, you should know basically what I just told you. The effects that some of these things will happen on the fitness over time graph. That is a great question for an exam, okay? So now that we know what our assignment is going to do, let's have a look at the code. So what do you actually have to do? Well, the thing you're going to have to do for the assignment is essentially this. So in the assignment, I have done this part for you. So I have initialized a random population, or a population with random individuals. I've done that already. I've written the loop for you, and you are not going to have any termination condition. So what you have to do is essentially this. You have to do this part of the genetic algorithm. And I've laid out the code in a really nice modular way so that you have the skeletons of all the functions, and you're given the settings object, and all you have to do is these parts, essentially. So when you open up your assignment, you will be given the following. So you have the following. I'm just going to go over the file list first, as I usually do. And then I will go over, I'll make the font a little bit bigger once we start with the coding. So don't worry about reading this right now. But the file list is as follows. Well, I've got the solution, so I'm not going to show you that. We've got a marks file. I'll go over the marks at the end. Again, we've got two user interface files. So we've got the GA GUI and the GUI. You don't need to worry about those at all. That's done for you. I have the index.html. Don't worry about that. The first thing that you do have to worry about is actually this Sudoku.js. So what I have done for you is I have included a data structure that holds the Sudoku board and does some calculations for you. So again, the Sudoku board, we talked about this last time. Even though it is being displayed and the game of Sudoku is a two-dimensional game, I am actually storing the Sudoku array as a one-dimensional array. All right, that's how I'm actually storing the array of values inside this engine. So if we look at the Sudoku class, that essentially stores it for you. The Sudoku class is going to take as its constructor a size. Okay, so that size is the size of the board. The square size is the square root of the size. So you got to make sure that when you construct this, you pass in a perfect square. And that's fine because that's all being done for you, right? The user interface is the thing that constructs these based on this slider here. So you don't need to worry about ever manually constructing Sudoku objects. In order for you to be able to get access to the particular value at a row or column, I've included that function for you, right? So getIndex row or column. So this function returns the index of the one-dimensional array associated with this row and column. So just to explain this again, we'll go back to the blackboard. So if we have a Sudoku board, let me make this text a little bit bigger. So here we go, 72. If I have a Sudoku board that looks like this, 1, 2, 2, 3, or whatever values we have, then remember, what I do is I take this Sudoku board that's 2 dimensions, and I essentially map this value to this index, this one to this index, this one to this index, this one to this index. So we go across rows and columns, or column first, or row first, or whatever, and the way that I map this row and column to this index of the 1D array is by calling this getIndex function. So you can use that if you want to, it's there. If you don't feel like you want to use it, don't use it. This function randomizes the Sudoku board. You may or may not want to have that. This function sets a particular row or column to a particular value. This gets the value of a particular row or column using the getIndex function. This function calculates the number of conflicts at a particular row or column, right? So that conflict, again, for the Sudoku is, does it conflict in a row? Does it conflict in a column? Does it conflict in a square? So that's a function that I've written that you can use if you want to use it. And also, you can construct a Sudoku board based on an input array, and this is the code that does that. So this is just a very simple holder of Sudoku information. That's all that it is. It's just a Sudoku board class, which is essentially a one-dimensional array with functions to allow you to access it by row and column index if you really want to. Okay, that has nothing to do with the genetic algorithm. I just wanted to show you that that's what that particular object is. Next, I want to show you the GA settings. So the GA settings file here contains a few things, but the first and most important thing is the GASettings class. So this class is going to store all of our variables that we are going to use throughout our genetic algorithm. For example, it is going to store the fitness function. And the really cool thing in JavaScript is that you can store you can store functions in a variable, right? So I can store the fitness function here, and I'll get back to that in a minute. I'm going to store the individual size. So the individual size, that is essentially the size of the one-dimensional array of our individual. So that individual size, for example, if we currently have this board, then the individual size is 9 times 9, which is 81. Okay? Down here, if it's 2 by 2, this is 4 by 4, which is 16. So that's what individual size is. It tells you the size of the array. Population size, currently set to 100. That is the number of individuals in your population. Very easy to understand. Elitism ratio, that is this slider right here. That is the percentage of genes surviving. But instead of being percentage, it's a ratio. So instead of being 10, it's 0.1. So it's on a sliding scale from 0 to 1. The mutation rate is here. That is currently set to 20%. The random ratio is here. That is currently set to 5%. So if you go back here and you reload, we have 20% for the individuals mutated. We have 5% for the random genes and 10% for the elite gene survival. And you can see that is exactly what's set right here. Okay. And whenever you modify this with the slider, you instantaneously modify this object and the user interface does that for you. So you never have to worry about changing any of the settings. You just play around with the user interface. The next thing that we have is an array called individual values. And what individual values is, it's an array of all the possible values that could possibly be assigned in this individual. So, for example, if you have a Sudoku board of size 9 by 9, then the possible values you could have are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So that's what that array stores. So that just tells you, hey, what integers are possible to be held in this genotype? And that's exactly what that's doing. The one other thing that the GASettings object has is a little helper function for you, which is get a random gene value. So for example, at some point, you're going to have to construct random genes, right? And in order to construct a random gene, you are going to have to get one of the random legal values for that gene. So for example, for a Sudoku board, a random legal value is any number between 1 and 9. But what we have here is we have stored all the legal values inside this individual values array. And so in order to get a random gene value, what you'll do is you'll generate a random number between, like, a random index of this array. Let me close this over here. So in order to get a random index for an array, you take the length of the array, you generate a random number between 0 and 1. That will give you a random floating point number between 0 and the length of your array, and then you have to floor that so that it becomes an integer index into your array. So what this does, it essentially selects a random value from this array. which is exactly what it says, get random gene value. So that function is there for you to use if you want to use that. So you can say settings.getRandomGeneValue, and you can start populating your array with random gene values. So that's the settings. It is modified by the user interface. You will never have to manually modify that anywhere in your code. The next thing that is inside this GASettings file is the sample fitness functions that I've given you. So here you see sum fitness, you see checker fitness, you see match row fitness, and you see match column fitness. And that is selectable right here in the user interface. So the user interface does that for you. It selects it. And when you select it, what it does is it takes this function and sets the value of this function. Okay. The reason this is currently underlined in yellow is because I have a function that's not in this class and I'm not using modules, so it doesn't know where this class is right now. But don't worry about that. It exists, trust me. It's just in another JS file. So if I had said here that this .fitness function equals sum fitness, okay, then what essentially happens is when you run your GA, you're going to be using the sum fitness function instead of the Sudoku fitness function. And again, that's handled by the user interface for you, but it's cool that you can store this function as a variable and then just call that function whenever you want to. So all these functions are just defined down here. They are going to be passed in the genotype array, which again is just the integer array that your Sudoku board is. And it's going to perform some sort of calculation and return that calculation as the fitness value. So just like sum fitness says, what does it do? Well, it goes through the array and it sums up the values and it returns the sum. Very, very easy. And you can see again, just to demonstrate that if we have some values selected, then what it does is over time, it maximizes that fitness. So if you take 9 as the maximum value, you have 81. What's 9 times 81? 729 or something like that. That's going to be our maximum possible fitness function. And so if we see here, we are almost there. We've got a few 8s left. Come on. Couple of 8s left. We got an 8 here. Oh, 729. We can get there. Maybe put in... Anyway, you can see what I'm saying. That's that fitness function. The other ones, I'm not going to explain because you can look at the code. Here is the checker fitness function. Here is the match row fitness function. And here is the match column fitness function. Really, really simple stuff. It just goes through the array and adds up things if they meet our criteria. But the important thing here to really realize is that the genetic algorithm does not change based on the problem that we are solving. Now, you could change it based on the problem we're solving, but I'm just trying to show you that the same GA with the same settings can solve multiple different problems based on the fitness function. And that's the really cool part of genetic algorithms, in my opinion, is that the fitness function is what's being solved and the algorithm just takes care of the rest. So that is the GASettings file. And this file is not to be modified by you. The only file that is to be modified by you, as usual, is this GA student file. So the GA student file is where you are going to be spending all of your time in this assignment. Now, there are a number of functions inside this GA student file, but essentially what all of those functions are the following. Your job is to do all of this stuff. What I have done is I have created a function called GAEvolve. So evolve one generation, right? Because this is one generation of a genetic algorithm. So all of this takes place inside that GAEvolve function, and that GAEvolve function is right here. It's the very first thing that you look at when you open this file. All of the other functions in this file that I have are select parents, do roulette wheel selection, that's a function. Combine parents to form an offspring, that's another function. Mutate the resulting offspring, that's another function. So your evolve function is going to look very much like this pseudocode. It's really nice. It's just going to call a few other functions. So knowing that that's what we have to do now, let's actually get into the code and we'll see what your GAEvolve is doing. So your to-do is to write this function. I've provided a skeleton code and a bunch of notes, and hopefully you can just go through 1, 2, 3, 4, 5, 6 and implement them all. But first, a very, very important note. What we've been saying so far is that a population is an array of individuals, for example. However, I do have one thing that has changed for this specific implementation. So the population is an array of JavaScript objects which contain 2 variables. So we don't have strictly an array of arrays. What we have is our population is an array of individuals. Each individual has 2 elements to it. It first has the gene, which is an array of integer values, and we also store the fitness along with the individual. So instead of, for example, having to have a population of array of just individuals and a separate fitness array, what I've done is just you have one object, it stores the genotype, which is the integer array, and it also stores the fitness value. So whenever you create a new gene, through whatever means, you create the integer array, you store that as the gene variable, and you calculate the fitness value, and you store that as the fitness number. So whenever you refer to something in the population, population_i.gene, that is the one-dimensional representation of the individual. So that's the phenotype, that's the array of integers. And then population_i.fitness, that is the fitness of the individual that gets calculated whenever you create your individual. Okay, so that's the population here. This variable is a JavaScript array of these objects. All right. So what does our GAEvolve do? Well, the GAEvolve does these things. So let's go through them one by one and tell you exactly what you have to do. The first thing you have to do is set up a new array which will hold the next population. So at any given time, essentially what happens is being passed into this function is the population and the settings. The settings is this object. So you can refer to all of these things with that settings thing. You get passed in a population of individuals. You get passed in a settings file. Your job is to create a new population and populate it with the next generation after having done all of this stuff. Okay, so the very first thing which I've actually done for you is let's just set up a new array which is blank, and we are going to fill it up with the next population somehow. So the very first thing that I recommend doing is, because we are going to be wanting to select things based on fitness, and this is not 100% necessary because it might be a little bit slow. Maybe you could find an optimization or something like that out there that would not have to do this. But I recommend sorting the population in descending order. So you'd end up with the highest population fitness individual first in the array and go all the way down to the least high or the lowest fitness individual in the array. So sort the population descending based on fitness. I am not going to give you the exact algorithm to do that, but just to reiterate, this is the fitness function that you're using. So if you're iterating through a population, you're using this fitness. If you are using a built-in JavaScript sorting function, you have to tell it that that is the fitness value that you want. But what you are sorting here is population. So somehow you sort, what the hell? Sort, why is it, stupid autocorrect? Sort the population. Okay, so if you come up with another function and you have this dot sort by fitness, if you want to population, that's what you can do. I didn't include this function skeleton because this is not a required step, but it's a very, very useful step. All right, so let's pretend that you've done that and now your population is sorted by fitness. So the next thing that you have to do step 3, is add the top N elite, meaning the top fitness individuals, to the next population. The percentage of elite genes to carry over is in settings.elitism ratio. Sorting the population array by fitness is the easiest way to do this, right? So what you have to do is you can calculate let num elite equal, well, how many elite am I going to actually have to carry over? Well, I'm going to do the following. I'm going to have a population dot length, right? Or I could also go into here and say settings dot population size. One of those two is fine. So settings dot population size. And then I'm going to multiply that by the elitism ratio. Okay, so those are my two settings. I'm going to take the population size, multiply it by the elitism ratio, and now I know how many elite things I want to carry over to the next generation. And just to show you how easy this step is, if you have sorted things properly, you can say for let I equals 0, I less than num elite, I plus plus. Since these are already sorted by highest fitness, then you can just say new population dot, and what is it, push for JavaScript. I go back and forth through many programming languages. So we're just pushing population I. Look at that. Or next population. That's why it didn't autocomplete. I've done that step for you. This is how you would do that if you have sorted it by fitness. And that's exactly what it is. So the number of things that you want to mutate, the number of things that you want to whatever, you just take the ratio and you multiply it by the population size. Super easy to do. Gonna delete that for now. Next step. Add the required number of random individuals to the next population. The percentage of random genes to carry over is the one given in settings.random ratio. So again, you'd take that random ratio, multiply it by the population size, and that's the number of ones that you want to add. You can get a random value by calling settings.getRandomGeneValue. Make sure you add the following object to the array whenever you're adding an individual. So I don't have a function here for this, do I? No, I don't. So here, what you're going to do is you're going to make a loop over the number of random things that you want to create. But how would you actually create a new individual, right? So you're going to say, let new individual equal, and so, or let's say let new gene equal this. I'll make sure I don't have a function for this. No, I don't. Great. So I'm going to create a new individual, right? The first thing I have to do is create the gene. And then how many random values do I want to put into this new gene? Well, that is in individual size. So all you have to do here for each required, for I don't want to give you the code. For the required number of things in the gene, add a new random gene value. Done. That's my gene. After I have the gene created, I'm going to say let new fitness equal settings.fitness function on new gene. Okay? So that is how I calculate the fitness of that thing. And then all I have to do is this. And I actually don't even need this. I've already done this for you. So you copy and paste this. This is new gene. And this is gene. Done. That step is done for you. Really, really easy. All you have to do is put it all together in JavaScript. Okay? So you're just creating the correct number of randomized genes that you're going to insert into the population. Now, the real meat of this comes in step 5, okay, which is the actual parent selection, the recombination, and the mutation. That's the real meat of the genetic algorithm. So, in this step, you are going to keep adding children until you fill the next population. So this step is going to be in a loop, right? So while next population is smaller than settings.population size, okay, I'm going to do these things. But the first thing I'm going to do is, in order to help me optimize this a little bit, if we go back to our roulette wheel selection algorithm, okay, remember, this is our roulette wheel selection algorithm, and I did an example in the last lecture of exactly how this algorithm works. One part of this algorithm is calculating the sum. So rather than calculate the sum every time we want to select a parent, we are first going to calculate the sum and just leave it there, store it as a variable. Then we are going to choose both of our parents. We are going to call this roulette wheel selection function, which gives you a population of individuals to select from and the sum of all the things in the population. So here in our roulette wheel selection function, we calculated the sum of the fitnesses, but in our assignment, we are going to be passed in that sum, so we don't have to calculate it every time. That's the only difference, okay? So now we're going to look at this roulette wheel selection algorithm. So you are given a population, you are given a fitness sum. What you're going to do is set up this variable, the selected index, and then you are going to use the algorithm from the slides and then return the selected index from the population. That's it. Okay? So you take this algorithm, and the population fitnesses are already in the population, right? So you don't create this, that's already done, that's inside the population. You don't create this, that's already done, that's passed in. So you're doing this part of this. So you do that, and you select a parent, and you return the population at that selection. That's it. So after you've done that, you've got parent 1 selected, and you've got parent 2 selected. And now what you have to do is, from those 2 parents, you are going to create 2 children. All right? And the way you do that is by crossover. So crossover, we are going to do the simplest form of crossover, which is you are going to be passed in 2 parents. You're going to take the first half of parent 1 and the second half of parent 2 and form a new gene. You're going to take the first half of parent 2 and the second half of parent 1 and form a new gene. Okay? If it's an odd number, then just take 1 to the left or right of the middle. Doesn't really matter. So that is this function, crossover. You take in parent 1, you take in parent 2, and you have the settings. And the reason you need settings is you need to calculate fitness. So you're going to have a new child gene that you're setting up. You add the first half of parent 1 to the child gene. You add the second half of parent 2 to the child gene. And remember that the size of the child gene must be equal to the size of the parent gene. Be very careful of this when the parent size is odd, because there's no exact half of a size. Choose 1 to the left or the right, it doesn't matter. Just make sure that the gene that you end up with, the child, is the same size as the parent. And then this line down here, you don't even need to change, okay? Because it's setting up the new individual, the new child, which has the child gene, and it calculates the fitness of the child gene. So that's it. All you've got to do here is the recombination, so that crossover, which is conceptually very, very simple. You just have to work with arrays a little bit. Once you have the 2 child genes, you then mutate the children, okay? So what you do here is you do something like this. So if the mutation rate has been satisfied, then you change some value to another random value. That is it. It could not be simpler. So down here, inside mutate individual, that's the function that you have to write. You say mutate changes a random index of the gene to a random gene value. And you already have a function which returns a random gene value. So the mutation chance is going to be if a random number between 0 and 1 is less than the mutation rate. So if the mutation rate right here is 20%, then we're storing that inside the GA settings as mutation rate, which is 0.2. So what we do in order to see if, a 20% chance has been hit, we generate a random number between 0 and 1, and if that is less than 0.2, that is going to happen exactly 20% of the time, right? So that is how we check to see if that mutation rate has been hit. So the mutation rate chance is if a random number between 0 and 1 is less than the mutation rate, this function modifies the individual. So of course, JavaScript is passed by reference, not passed by value. So all I have to do is take a random index of the individual and set it to a new random gene value. That's all I have to do in Mutate Individual. So we've done roulette wheel selection, we've done crossover, we've done the mutating of the individual, and the last thing we have to do is add the children to the population. And the only tricky thing here is that you've created 2 children. Normally you're going to add 2 children to the population. But for example, if you currently have a population of size 100 and you currently have 99 things in that population, you would not add both of the children, you would only add one of the children. So it says, be careful not to add child 2 if that would push you above the population size. And so the next population array should always be the same length as settings.population size. And reminder here, always return next population. So the first thing you do is return this. The only reason I don't have it there is because in order for like the code to not crash on a blank array, I have to put in that it's returning the previous population. So that's it. That's it for the GA. It's so easy when I've given you this framework, right? You just have to write those few functions. The very last thing that I want you to do for this assignment is the following thing. Here is the Sudoku fitness function. You have seen from me doing this that the Sudoku fitness function, it doesn't work very well. It basically counts the number of conflicts, right? And that's, well, it's kind of the opposite of that. So I want you to go into this Sudoku fitness function, and I want you to try and modify this. So see if you can modify this function to make your GA solve a 9x9 Sudoku. That would be your ultimate goal for this assignment. If you don't solve a 9x9 Sudoku, that's okay. You can see here that my sample solution isn't solving it in an instantaneous amount of time. But I would like to see how close you can get to solving this. Now, your 2x2 should be solved, right? 2x2 is a very easy problem. It should be solved within, a number of seconds. Oh, and by the way, I'm running this in Firefox. This is like 10 times faster in Chrome. So we will be marking it with Chrome. I just don't particularly like Chrome, so I'm not using it for this demonstration. But if you want the fastest code, run it in Chrome. Here is the Sudoku fitness. What it does, it adds up. Oh, okay. So this is the way the Sudoku fitness works. It adds up the number of unique things in each row, the number of unique things in each column, and the number of unique things in each square. And then it adds all of those together, and that's the fitness. Can you do better than that? Probably. I want to see what you come up with. And when you do come up with a better fitness function, I want you to create a comment. So remove these comments and then say, here's what this does. So explain to me in English what this thing actually does. Okay, I'm going to delete this code here that I've already written. And so that's the only thing that's left, is I want you to look at this fitness function and try and come up with something a little bit better. So that being all that you have to do in the assignment, let's look at the marks. So we've got 5% for code style, blah, blah, blah. You've got the following for GA functionality. So your GA functionality, you should solve the 2x2 Sudoku puzzle very easily. It should make progress towards solving a 3x3 Sudoku. It should get pretty close to solving a 3x3 Sudoku. it should very easily solve all of the non-Sudoku fitnesses for 9x9. What I mean by that is if I click any of these, within 30 seconds to a minute, you are solving all of the non-Sudoku fitnesses. All right, you can see here that this is very easily solving these values. And now, geez, it's so much faster in Chrome. So use Chrome for your assignment. And then the graph of fitness over time makes intuitive sense. If with the default values, you are not getting something that looks like this with the max on top, the average in the middle, and the min on bottom, you're doing something wrong. And that is how I'm going to be able to look at your algorithm and within 10 seconds know if your GA is working correctly or not. Then for the individual functions, I've got just marks. Oops. That's from a previous version of the course. So elite survival, random individuals, child generation, you've got the roulette wheel, the crossover, the mutation rate, correctly fills up next population, Sudoku fitness modified, and the modifications explained in the comment above the function. That is all, that's the assignment, all right? Pretty straightforward marking scheme, pretty straightforward assignment. You just load up GA student and you start going down from 1 to n until your GA works. That's it. That's the assignment. You can explore the user interface if you want to, if you're interested, but that's basically all that you have to do. The only other thing I want to show you is if you did want to look at this, inside the, there's a reset function in the user interface which resets everything. That's called whenever you change, like, for example, the size of the board, it resets it. Inside that function, this is the code that sets up the initial random population. Okay, so you can see that it sets up, it calls this generation is generation 0. We have a new blank population. For the population size, set up some random genes and then push those genes into the population. If you want to have a look at how my code generates random genes, there it is. And when you go to generate random genes inside your function, right here, the random individuals, you can look at my code as inspiration for that if you want to. Don't copy and paste it though. Just write it yourself and know how it works. And just as a last thing, any of these functions that you are doing for this assignment, I can ask you to put in pseudocode on the final exam. Okay, so any of these functions are pseudocode of these is perfectly fair game for the final exam. And very, very finally, remember that assignment 2 is due tonight. Assignment 4 may not be available for download until tomorrow. Okay, so I wasn't going to release it until midnight tonight anyway, and I'm sure nobody with 3 weeks is itching to do this tonight, but assignment 1 will be available at some point tomorrow, Wednesday. Okay, so great. Thank you so much. Someone had a question. Do we need to worry about duplicate values in the children? I'm not exactly sure what you mean by that, but no, you do not need to check duplicate values. You're just letting the GA do its thing. So you are selecting parents, you're recombining them, you're mutating them. If there happen to be some duplicate values, whatever. That's the way she goes, right? Okay, no other questions. That's it. So I guess it took an hour, but I wanted to give you as much detail as possible. This assignment is not the hardest thing in the world, but do not wait until the last day for it because maybe you have some problems with arrays, you have to ask me questions about it, etc. All right. See you in the next one on Thursday when we start talking about reinforcement learning, which is super exciting and I can't wait to teach you about it.